brought to you by PBS, and this is Fair Use. Let's go. We about to get it in with
you and I belong to the only group of hominins on the planet Earth today. We are the lone twig left on our branch of the family tree. But we weren't always alone. 100,000 years ago, Eurasia was home to...
He gonna drop a few bombs, so pay attention and listen up. Now, listen up. He gonna drop it about sub-Saharan Africans, and Neanderthals.
Other hominin species, some of which we know our ancestors met and spent some quality time with. Some of them we've known about for a while, like the Neanderthals, whose fossils we've been digging up since the 1800s, but some of them are more recent additions to the family tree, like the Denisovans, who we may, on this channel, have called Denisovans, but we have been informed that it's Denisovans. The Denisovans were discovered almost by accident in 2008, and we know them only from a few fossil bones and from the DNA of their living descendants. That surprising discovery has opened our eyes to the fact that our ancestors met and even mated with other hominins. So anthropologists are following the genetic traces of these ancient interbreeding events, traces that many of us carry with us today. Thanks to this research, we're starting to better understand how and even where modern humans paired up with other hominins, giving us a more complete picture of the history of our species. And we're starting to tackle some really exciting questions, like what's our inheritance from that time when we met up with other human species, and why are we the only ones left today? As we get closer to answering those questions, we're starting to see that maybe part of our success as a species has to do with those other hominins that we encountered in our travels around the planet. Neanderthals lived throughout Europe and from southwestern to Central Asia. We found their fossils from Portugal and the UK in the west, all the way to the Altai mountains of Siberia in the east, and down to Israel in the south. The oldest Neanderthal-like fossils come from a site in northern Spain called Cima de los Huesos, literally the pit of the bones, dated to about 450,000 years ago, while the most recent come from a handful of sites across Western Europe that date to around 40,000 years ago. Anatomically, the Neanderthals were very much like us, with few differences. They were relatively short and stocky, with robust limbs and big brains. They had heavy brow ridges, large noses, and brain cases with more of an oval shape than the round ones of Homo sapiens. And we know that they weren't just dumb cavemen. They controlled fire, made stone tools and spears, made jewelry from eagle talons, and cared for injured members of their groups. And our ancestors clearly recognized them as being like us, enough so that we interbred with them. We know this because researchers have sequenced the Neanderthal nuclear genome, originally in 2010 from bone fragments found in a cave in Croatia. And by comparing that genome to those of modern humans from many different populations, we can find out how much Neanderthal DNA some of us still carry. Although original estimates were around 4%, more recent studies have suggested that living people of European and East Asian descent have between 1 to 2% Neanderthal DNA in their genes. Meanwhile, people native to sub-Saharan Africa don't have any Neanderthal DNA, indicating that their ancestors never encountered Neanderthals. As we find more fossils to sample, we can tell that these interbreeding encounters happened more than once, and our genomes can even shed some light on when they happened. For example, genetic material extracted from the left femur of a modern human male who lived in Siberia around 45,000 years ago has been found to contain Neanderthal DNA. And researchers were able to measure how long the Neanderthal segments of his genome were compared to the same segments in living people. It turned out his Neanderthal sections were longer than modern humans, suggesting that he wasn't that many generations removed from his Neanderthal ancestor. In fact, the researchers were able to estimate that this Siberian man was the product of an interbreeding event between Neanderthals and Homo sapiens that occurred 50,000 to 60,000 years ago, just 10,000 years before he was born, give or take a few thousand years. And this was likely when modern humans migrating out of Africa encountered Neanderthals in the Middle least. Likewise, a 40,000-year-old jawbone was found in Romania in 2002, which provided some of the earliest evidence of modern humans in Europe, and it was found to have some anatomical similarities to Neanderthals. When its genome was sequenced over a decade later, that human was found to have had a Neanderthal ancestor only some 4 to 6 generations back. Between 6 and 9% of its genome was Neanderthal. So using fossils like these, researchers have been able to determine that Homo sapiens bred with Neanderthals several times in different places. But how did all of this interbreeding change us? Well, sometimes not very much. The genome from that Romanian jawbone suggested that population didn't contribute much to the DNA of living modern humans. But sometimes these encounters had a big impact. For example, 2 genes that play important roles in our immune response system seem to have passed from Neanderthals to people of Eurasian descent. One of these genes, known as STAT2, is part of our immune system's signaling response when we get a viral infection. And we know that the Eurasian version of STAT2 comes from Neanderthals because it isn't found in sub-Saharan Africans. Plus, molecular clock studies have found that the Neanderthal version of this gene appeared in the Eurasian genome long after the evolutionary split between Homo sapiens and Neanderthals, so it must have come from interbreeding. Meanwhile, members of many East Asian populations have been found to carry a gene known as HYAL2, which is involved in skin cell repair after skin has been exposed to the sun's UVB rays. In other words, a sunburn, and this gene also seems to have come from the Neanderthals, likely a helpful adaptation for modern humans spreading across Asia. These genes are both examples of a phenomenon known as adaptive introgression, where genetic material from one species moves into the gene pool of another species and then is selected for so it sticks around. But these genetic contributions can also have a downside. Introgressed genes that were once beneficial can become less so over time as the environment in which natural selection is taking place changes. For example, there's a gene that's involved in the rapid coagulation of blood, which used to be really beneficial before medical care was available, but also that gene increases the risk of blood clots, and this gene too seems to have come from interbreeding with Neanderthals. But importantly, Neanderthals are not the only hominins that we got to know so intimately. In 2010, paleogeneticists announced a shocking discovery. A site known as Denisova Cave in southern Siberia had yielded ancient mitochondrial DNA from a previously unknown hominin. Earlier work there had turned up evidence of modern humans and Neanderthals, so the researchers were expecting that the DNA they extracted from a pinky bone found there would also be Neanderthal. But it was not. Almost a decade later, we have 7 fossil bones with this unique genetic signature. There's the tip of a pinky, there's 3 molars, a sliver of long bone, and a piece of skull cap, all from Denisova Cave, all dated to between about 52,000 to 195,000 years ago. And there's also a single partial jawbone from the Tibetan Plateau, dated to at least 160,000 years ago. This new group of hominins has yet to be given a scientific name because it lacks a type specimen, a fossil that's complete enough for future finds to be compared to. So for now, they are informally known as Denisovans, and they are essentially a ghost lineage within our own ancestry, a branch of the hominin family tree that lacks a fossil record. Now, it could be that there are other Denisovan fossils in collections around the world that just haven't been identified. But because there's no type specimen and most fossils don't have DNA that can be extracted, we just don't know for sure. But we have sequenced enough of the Denisovan genome to be able to tell some of their story. For instance, their mitochondrial DNA, which is passed down from mothers to their offspring, suggests that the last common ancestor that we shared with the Denisovans lived about 1 million years ago. But the nuclear DNA of Denisovans, which accounts for most of their genome, is actually more similar to ours. So this might be a sign that Denisovans also interbred with some other hominins within our lineage, like Homo erectus. Today, we find small amounts of Denisovan DNA in populations in East and South Asia, and up to 6% Denisovan DNA in some populations of Melanesians in the Southwest Pacific. genetic. And the variations we see between the DNA and modern people and the ancient genomes we have from Denisovan fossils suggests that there were interbreeding events with at least 3 different groups of Denisovans, so it didn't happen just once or in just one place. And some of these genetic contributions are really important. Take the gene known as EPAS1, found in many people native to the Tibetan Plateau. This gene is associated with differences in hemoglobin concentrations, and at high altitudes, more hemoglobin means more efficient oxygen transport. This gene seems to have been introduced by the Denisovans and was strongly selected for because of the advantages it offered to modern humans living at high elevations. So we know that many of the hominins that we used to live and hang around with were really well suited to a lot of environments. So, why aren't there populations of these other hominins walking around today? Well, anthropologists have been thinking about that for a long time, especially when it comes to the Neanderthals. The longest standing explanations for their disappearance have been that climate change, competition from modern humans, or some combination of the two caused their downfall. And there's evidence that there were cycles of intense cold and dryness in Europe between 44,000 and 40,000 years ago, which might have caused Neanderthal populations to decline, leaving them vulnerable to extinction. Other researchers have modeled the distribution of Neanderthals and their habitats and suggest that those habitats were becoming more fragmented by changes in climate. As for the impact of modern humans, we know that we met Neanderthals, but there's no evidence of violence or direct competition between the two groups. So some researchers have suggested that it was just the continued migration of modern humans from Africa into Eurasia that pushed Neanderthals into extinction, and that we weren't better adapted than they were, we were just more numerous. Other researchers think it might have been that we had better clothing and technology, and that social factors like long-distance trade may have given us an advantage. Or maybe the Neanderthals were just on their way out anyway. The genetic information we have suggests that their populations were smaller than those of modern humans, and that inbreeding might have occurred more often, resulting in decreased genetic diversity. This generally makes populations less adaptable to changing environmental pressures. As for the Denisovans, well, we only just realized that they existed at all, but it's possible that some of the same factors that brought about the end of the Neanderthals affected them as well. And as a result, we are the only species of hominins left. But it's kind of remarkable to me how close we were to that not being the case. But this doesn't necessarily mean that Homo sapiens was somehow more fit for survival from the start, because we really weren't. The fact is, our species became better adapted to local conditions precisely because we interbred with other hominins that had evolved to fit those environments. The other species, like the Neanderthals and the Denisovans, contributed to our survival in these new landscapes. They helped us tolerate new conditions like high elevations and intense sunlight. They helped our bodies become better at signaling when we were sick, and they helped our blood clot faster when we were injured. The genetic legacy they left us is part of the secret of our success. And in a sense, those hominins didn't completely disappear, because parts of them live on today in us. They live on in our own genes, reminding us of a time when we weren't alone.